Hello everyone. Today I'm going to talk about faster min plus product for monotone instances. This is joint work with Shucheng, Professor Duan, and Tianle. Let's first see the problem definitions. Min plus product is one of the most basic problems in the field of fine-grained complexity. It is known to be equivalent to all-pair shortest path. The fastest runtime is slightly subcubic by Williams in 2018. It is widely believed that this is near optimal. Although min plus product is hard in general, there are special cases where faster algorithms exist. The most well-known example is when both matrices have small bounded entries, and in this case, the min plus product can be computed in subcubic time. There are examples where matrices have more structures. In 2016, Bremen et al. Studied fast algorithms for the so-called bounded difference matrices. In 2020, Vasilevska-Williams and Xu studied monotone matrices. Let's introduce these two notions next. An integer matrix is bounded difference if adjacent entries differ by at most 1. In this problem, we want to compute min plus product when both input matrices have bounded difference. Despite the direct connection between min plus product and all-pair shortest path, its actual applications are in the string literature. In the paper by Bremen et al., they showed bounded difference min plus product can be used to solve language edit distance and RNA folding. In a recent paper by Mao, bounded difference min plus product was used in tree edit distance. Also, in a more recent paper by Fried et al., bounded difference min plus product has applications in computing Dick edit distance. A matrix is called monotone if each row of the matrix is monotone, plus that all entries are non-negative and bounded by order n. In this problem, we want to compute min plus product when only matrix B is monotone. And here we do not assume anything about matrix A. It is known that this definition is a generalization of the previous bounded difference min plus product. Also, other than applications in string problems, it has application in the classical single source shortest path problem with negative weights. Besides min plus computation between matrices, we can also define min plus computation between sequences. More specifically, given two integer arrays, we can define min plus convolution between these two arrays using this formula. The textbook algorithm for this problem has quadratic time, and the fastest runtime so far for min plus convolution is better by a subpolynomial factor. It is believed that no truly subquadratic time algorithms exist. In the monotone setting of min plus convolution, we assume that both input sequences are non-decreasing and bounded by order n. This problem has applications in many other problems, for example, histogram indexing and necklace alignment. This table summarizes all the runtime complexities on different versions of min plus product problems. The baseline for matrix product is cubic, and for convolution problems it is quadratic. In a paper by Chang and Levinstein in 2015, they had the first subquadratic time algorithm with runtime n to the 1.859. The algorithm by Bremen et al. In 2016 was the first to achieve subcubic time n to the 2.824 for a bounded difference min-plus product. Later on, Vasilevska, Williams, and Xu generalized the subcubic runtime to the case of monotone min-plus product, which has a slightly larger runtime of n to the 15 plus omega over 6. Here, omega refers to the fast matrix multiplication exponent. This runtime was further improved to n to the 12 plus omega over 6 by a follow-up paper by Gu et al. In a recent paper, Shi, Duan, and Xie revisited the bounded difference min-plus problem, in which they developed new techniques to achieve a much clearer improvement of n to the 2 plus omega over 3. This paper today is a follow-up work of their result. First, we improved the previous upper bound on bounded difference min-plus product from 2 plus omega over 3 to 3 plus omega over 2. In fact, our algorithm works in the more general setting of monotone min-plus product. Secondly, we also study the min-plus convolution problem and achieve a clean subquadratic runtime of n to the 1.5. In this talk, I will only focus on this runtime upper bound. I will first describe a toy version of our algorithm, which achieves a weaker bound of 2 plus omega over 3. For the rest of this talk, let's assume for simplicity that the fast matrix multiplication exponent is 2. The first step is to estimate the min-plus product up to some sublinear additive errors. This is common in all previous works. The way of doing this is by rounding all entries to integer multiples of n to the 1/3, and then compute the min-plus product between two quotient matrices. Since all entries become smaller, the min-plus product between rounded matrices can be computed in subcubic time. In particular, the runtime is n to the 8/3. In the first step, we have decomposed entries as sum of quotients and remainders. To use the approximation matrix tilde C, the basic idea is to focus on those indices where the sum of quotients of A and B are equal to tilde C. And then only under this condition do we minimize the sum of the remainders. The idea is to separate quotients and remainders using bivariate polynomials, where exponent of x are remainders and the exponents of y are quotients. Suppose we can compute the product between these two polynomial matrices. Then we can expand each entry of C as a sum of polynomials ordered in terms of y degrees. Then, since we only care about terms where sum of quotients of matrices A plus B is equal to the corresponding tilde C, we should ignore all the higher order terms in terms of y degrees and focus on the minimum x degrees in the first several terms. It is guaranteed that we can recover the min-plus product result by looking at the minimum x degrees of these red x terms. However, matrix product between the two polynomial matrices is no easier than the original min plus product. The runtime here is n squared times the maximum degree of x times the maximum degree of y, which is still n cube. The key idea here is to reduce y degrees by taking modulo p. That is, instead of multiplying the two original polynomial matrices, we multiply two polynomial matrices where y degrees are replaced by the remainders modulo p. Here p is a prime number. Now, the maximum degree of y becomes at most p, so the runtime becomes n to the 2 plus 1/3 times p, which is subcubic when p is small. When there were no mod p operations, we're looking for minimum x degrees among the red univariate polynomials. But now, mod p operations add extra noise to the output polynomial matrices. For the desired y degree, we have merged with red univariate polynomials with some other univariate polynomials whose original y degree was larger but with the same modulo p residue. In other words, we can view this mod p operation as a hash function that puts multiple x polynomials in the same y bucket. To extract the true answers, we need to do some post-processing of our polynomial matrix multiplication. Namely, we will identify all the erroneous terms and subtract these extra yellow polynomials. The reason why error subtraction can be done fast is that the total number of error terms is small when the prime p is uniformly random. Quantitatively, we show that when p is of order n to the 1/3, the total number of error terms is n to the 3 minus 1/3. The proof is very simple. Fix any triple of indices such that the quotients of a plus b is very close to the quotient of c. We ask, what's the probability that they are somehow close as well under modulo p? Since p is a random prime of order 1/3, this probability is inverse in p, which is n to the minus 1/3. So far, we have not used the fact that b is monotone. This property will help us locating all the error terms in the end. After fixing the random prime p, recall our goal is to find all triples such that the difference is not a constant, but it is a constant under modulo p. Notice that when I, k are fixed, what we need to do is to list all j that meets both properties. Now, since the row is monotone, all the tilde b entries are at most n to the 2/3, so we can group all the consecutive equal entries as intervals. For each of the n to the 2/3 intervals, since all entries are the same, we can preprocess matrix tilde c and list all j's using standard interval data structures. Now, we are ready to describe our full-fledged algorithm that achieves the exponent of 3 plus omega over 2. One bottleneck of our previous algorithm is computing the approximation matrix in the first place. A natural idea is to compute it in a recursive manner and gradually scale all the values bit by bit. Hopefully, we can reduce the time to n squared times p, which is n to the 2.5 if we choose p to be order root n. More specifically, consider different numerical values of all the entries, and we can define a sequence of polynomial matrices using the previous approach. Then, for each pair of the polynomial matrices, we want to compute their product to reveal the same scale of C. As before, since mod P brings about error terms, we need to maintain all triples with these two requirements throughout the recursion. Unfortunately, these triples cannot be maintained efficiently as we hoped. Suppose during the ith level, we want to find all triples such that this formula is 1 under mod P. Then it is more or less equivalent to retrieve triples from the L plus 1th level, which are 2 to the minus 1 under mod P. However, in the previous L plus 1 level, we only have triples whose value such that we only have triples where this formula is constant under mod P, which can be far away from 2 to the minus 1. Let's describe this issue with a picture. Here, we have drawn an axis of mod P. For the purpose of recursion, hopefully, we want all delta values to lie in this red region, so that each level can reuse the information from the previous level. However, since division by 2 is not always shrinking, the delta values could be jumping around like this, which is out of control. The key to circumvent this issue is that instead of scaling entry values, we only scale the residues. Previously, we were considering values like this sequence and take mod P on the y degrees for each pair of polynomial matrices. Now, we first decompose A and B as quotients and remainders mod P at the beginning, and then consider different scales of only the remainders. Note that here we are not taking any modular operations on the polynomials anymore. The mod P operations are done at the beginning once and for all. At different levels of recursion, we want to compute different scales of the remainders of the output values of matrix C. As we have done before, here we also need to find the minimum remainders under the condition that the quotients are matched with the approximation matrix tilde C. Recall that we need to maintain all erroneous terms throughout the recursion. As for the previous issue, suppose we want to find triples that satisfy this equality. Then it suffices to find triples from the previous level where the difference is divided by 2. Now, the key point is that this is integer division by 2, not field division under mod P. So it must have been maintained already in previous levels. Now, let's elaborate more on the implementation details. Recall that our goal is to maintain all triples that satisfy this red equality and this yellow inequality. As a sanity check, note that if we don't do any recursion, then when P is a prime, the probability that the equality holds is 1 over n squared. So the total number of triples is already bounded by n to the 2.5. Well, this does not directly give an n to the 2.5 runtime because locating all the k indices still requires non-trivial recursions. Now, let's consider a general recursion level, L. By definition of variables t, r, and s, which are the remainders of a, b, c, it is equivalent to a plus b minus c is at most of order 2 to the L under mod p. By a union bound over all n to the 2 to the L possible values of the remainder, the probability is at most 2 to the L times n to the minus half. So the total number of errors is at most 2 to the L times n cubed over p. Compared with the earlier algorithm, where there are no recursions, here is an extra factor of 2 to the L. Namely, for early levels of recursion where L is large, the total number of errors can be as large as n cubed, which is bad. The key observation is that since B is monotone, we can partition the rows into n over 2 to the L intervals, such that each interval shares the same value. Then we can group these triples together. In other words, although the number of triples is larger by a factor of 2 to the L, this extra factor can be cancelled by grouping intervals. When we are subtracting erroneous terms, we can apply some efficient data structures to do the subtractions for all polynomials simultaneously for all indices j from the same interval. Therefore, the runtime is proportional to the number of index interval triples, other than the original number of index triples. One last detail is how to maintain all the index interval triples. The key property here is that index interval triples at the current level of recursion is a refinement of triples from the previous level, and so we can maintain them efficiently. Thanks for listening.